Hello, and welcome to Tech to Tech presented by KYZEN, where we will explore common cleaning questions and answers. Let's get started. I would like to introduce KYZEN's own Ethan Mueller.
Thank you, William. Welcome back to Tech to Tech. Today we're going to be discussing rapid drying of complex geometry parts. So what does that mean? We're going to be discussing some of the processes that involves part drying, and we're going to discuss some of the best practices and some of the challenges that we may face when we're attempting to dry parts. So where do some of these challenges come from? When we're talking about a cleaning process, one of the most critical and sometimes challenging parts of the overall cleaning process can be the drying segment. So what factors into this? What causes our problems? The overlying process design, the process as a whole. What is our chemical solution? Are we using a solvent process, or are we using an aqueous-based process? How are we racking our parts? Are they densely packed into baskets? Are there features that hold solution that carry that solution through the machine that we're racking up? Is there a way we can rack it down? What does the drying process look like? Are we just using a simplistic air knife process, or are we going into a heated blow-off, or are we in a solvent process where we're just relying on the solvent to evaporate away? And then, one of the biggest challenges of drying a part can be the part itself. What is the design of the part? What does that look like? Does it have complex features, narrow features, or maybe parts of the assembly are sensitive to temperature? All things that we need to consider when we're looking at implementing a new cleaning process, a new piece of equipment. So the considerations, first and foremost, again, we want to look at the complexity of the part. If we have a complex part, that's going to kind of dictate the way that we need to go to actually ultimately dry this part. And if we're dealing with a part that has a lot of complex features and geometries, we might want to focus on a solvent-based process where that solvent has a relatively low surface tension and tends to be more on the volatile side of things, where volatile things tend to evaporate away much more favorably than less volatile things. We need to consider what kind of throughput do we need. If we are looking at an aqueous process, that takes a little bit longer to dry. And so if we have to have these complex parts dried relatively quickly so that we can meet our throughput, that's all things that we need to consider when we're looking at a process. And of course, we need to look at cost. Solvent tends to be costly. Evaporating water tends to be costly. And we need to think about the safety of our personnel and our operators. When it comes to drying, or improperly drying, I should say, that can lead to multiple different issues. First and foremost, you can have oxidation on your parts. This can lead to downstream issues such as paint adhesion or adhesion of other materials. It can lead to improper gauging if we're trying to take measurements of our parts. And it can lead to packaging or storage issues. Maybe we put the parts away and they're looking good, and then we send them to our customer and they're no longer looking good anymore. In addition, if we're not properly, specifically more so with aqueous process, if we're not effectively removing that liquid, the solution, that can lead to water spotting or other residue issues. And all of these issues can lead to scrap or rework, which is obviously undesirable. Your typical aqueous drying process, it looks like a water strip or some sort of air knife where you're using air to strip that water away from the part. And then depending on the piece of equipment that you go with, you maybe have a heated blow-off where you're actually moving hot air past the part. The water strip is to sheet the water away. The heated blow-off is to actually evaporate any remaining water. And then sometimes, depending on what the downstream process is, these parts might have to go into a bake process. And I've seen where people do this for both aqueous and solvent processes because they want to ensure that there is absolutely no liquid remaining on the surface before they go into that downstream process. There is equipment out there that does vacuum dry. There's some aqueous equipment that has this feature, and there's also a vacuum degreasing technology that utilizes a vacuum drying. And essentially, what that's doing is you have your parts in a chamber, you close that chamber off, and you pull a vacuum over it, and that vacuum is effectively pulling that liquid from the chamber and away from the surface of your part. When it comes to drying, we really want to think about our fixturing, how we're running our parts through our machine. Again, if you have a part that can hold solution and pull that through the machine, you want to do everything you can to flip it so that it's not carrying solution through. Not always possible, but we need to make our best attempt here to do this. If we can't make that possible, again, we might need to, when we're implementing this process, we may need to consider that beforehand and go with a different type of process or add some features that allow us to maybe rotate the part to dump it out. The throughput, again, we really need to think about throughput when we're thinking about drying. Drying can be a limiting factor in the cleaning process, and so something that needs to be sorted out prior to making an investment. The process temp. A lot of times you can increase the temperature of your process to speed up how quickly something dries. Of course, some things are sensitive to temperature. Aluminum, plastics tend to have temperature sensitivity. Something needs to be considered ahead of time. And then the overall effectiveness of our drying process. Some people need their parts to be completely dry. Other people can allow their parts to come out of the machine and maybe air dry for a little while prior to packaging or whatever the next downstream process is. So again, when you're looking at a new piece of equipment, consider all these things before you actually decide what you're going to go with. Solvent drying. Won't make any bones about it. Solvent dries much more quickly and much more effectively than aqueous does. You can use solvent as a water displacement method where you actually go into an aqueous process for whatever reason. Maybe you need aqueous to clean and you move from that process to a solvent process to actively displace that water. And now the water's gone, but the solvent's on the surface, the part comes out, the solvent evaporates away. Solvent has a low surface tension, which, as you can see by this image, it allows solvent to get into tighter spaces, which is half the battle. And then the other battle is getting them to get in there, clean the material, and then come back out to where it's no longer in that tight space. The low surface tension is definitely helpful for accomplishing that purpose. In addition, solvents are volatile, and so they're more prone to evaporate away and to come away from the surface of the part. And another nice thing is solvents rely on solvency to clean, whereas water processes rely on wetting agents and surfactants and saponifiers, and these things are in NVR. So a solvent relies on solvency, and that is a zero NVR process, so it evaporates away after you're done with it. Whereas the water relies on all those other things, which is an NVR. The water evaporates away, but the NVR stays at the surface of the part. So that can cause us some issues, and something that we want to consider: how critically clean do we need our parts? And then just kind of one more nuance beyond on the solvent side of things. There's vacuum degreasing and there is vapor degreasing. Vapor degreasing is a traditional method where you are putting a part down into an open top degreaser. There's heating on the bottom. It's boiling the solvent, turning it into a vapor, and then coming up to the part which is in a cooled area. There's refrigeration coils around the part, and it's coming up, it condenses on the part and drips back into the machine, and it just kind of does that repetitively, and there's a process. And the solvents that are used in these tend to be volatile, low surface tension, so they get in the part, they come back out of the part, they evaporate away very quickly. The vacuum process is a little bit different. You put the parts in a chamber, pull a vacuum over that chamber, you introduce the solvent so there's no gas in there. The solvent does have a relatively low surface tension, not as much as the solvents that are used in vapor top degreasers, open top vapor degreasers. and they also have a much higher boiling point and are less volatile. So that type of solvent cleaning is relying on the vacuum to actively pull that solvent away from the surface of the part, which, even though it has a little bit higher of a surface tension, a little bit less volatile, higher boiling point, it still tends to dry better. These systems tend to dry better than an aqueous system. Some of the challenges that are associated with these processes, for aqueous specific, it's really energy intensive to dry water, to evaporate water away. Again, we want to try to sheet that water away as much as we can and then evaporate it. There's some throughput. Trying to remedy throughput by increasing temperature isn't always an adoptable solution. It might hurt our parts. The surface tension of our aqueous solution tends to be relatively high. It doesn't get into those crevices, and then it's harder to get back out. And the volatility of it, the high surface tension, just is not conducive to a rapid drying process. And again, aqueous tends to leave more water spots and residues on the surface of our part because it's relying on all those other things to clean, where solvent is relying on solvency. There are challenges, of course, with solvent. There's a lot of situations where somebody's going to take an aqueous process over a solvent process, even when they need to, have a critically dry part. The cost of equipment can be a barrier to entry. The overall cost of solvent can be a decision that maybe steers you towards a different process. And then the environmental side of things, the environmental health and safety side of things, the reporting that we might have to do, the compliance that we need to be, we need to achieve a certain level of compliance, operator exposure, and then we need to ultimately dispose of these materials once they've come to end of life. So just to kind of wrap everything up here, getting into a best practice, when we have complicated parts that we really need to be able to dry before moving on to the next process, solvent is always going to be a better choice for drying. If you do need to use an aqueous process, you can implement a solvent process downstream as a water displacement method. We want to take precaution when we're putting our parts through the system, not only for maximum cleaning efficacy, but we also want that we don't want those parts to carry solution from stage to stage within our washer. So we want cupping features to be focused down, or we want to fully rotate our basket or our part so that if there is a cupping feature on, where I can't get away from it, where I can dump that part out, whatever we need to do to get that solution to come out before it progresses on to the next stage. And it's easiest to dry in the machine. Some people, again, maybe have the option of allowing somewhat wet parts to come out, and then they can allow them to air dry in their facility. A lot of people don't have that option. Drying to completion in the machine, that means setting up the right processes and doing the right things. It's all part of it. Something that you can do is you can use positive flow, which is basically directing air or something through the intricacies of the part to aid in getting that solution out of those complex features. In conclusion, failure to dry ultimately is likely going to lead to scrap or the need to rework a part. Obviously, that's undesirable, costs money, takes time, reduces our throughput, upsets our customers. When we're looking at a process or we're wanting to change a process, we want to focus on the overall design of things. And there's a lot of levers we can pull with an existing process. And there's a lot of different processes we can choose from up front so that we're getting the right thing and it's matching our needs. Again, solvent is always going to dry better and faster than aqueous is. And NVR from our aqueous solution is going to result in residue on the part, which can lead to a failing QC. Some frequently asked questions on the topic: how can I improve my existing drying process? You can look to maybe make some investments in increasing the overall flow, number of air knives in an aqueous process, or you can look for to implement that solvent, that downstream solvent process where you're using it for water displacement. There's a lot of different ways that you can improve the process. It's just dependent on what you have and what you're going for. Can I use acetone or IPA for water displacement? Yes, you can absolutely do this. These are commonly used commodity-based products. I would just be careful with these. They are flammable. They are very volatile. They stink. So you can use them, but there's other better options out there on the market that maybe even prove more cost-effective than these commodity-based materials. Can I use mineral spirits for water displacement drying? Yeah, water or mineral spirits are often used in this type of way. Mineral spirits are not very volatile and they don't dry quickly. So it really depends on what your downstream process is. If you need a dry part that does not have any liquid on it, this is probably not the best way for you. It can prevent other issues that are associated with water, such as the corrosion issues, where you have this slow evaporating liquid on your part that does not cause rusting, but it's not really to aid in quicker drying. It's more to displace that water to prevent the water from creating corrosion, and then eventually you go to your downstream process, and hopefully by then it has completely evaporated away. Can I implement a vacuum degreasing system after an aqueous cleaning process? I would say in most situations, you could replace your aqueous process with the vacuum degreaser. If you were going to do this, if you were going to put a vacuum degreaser right after an aqueous process, you'd almost be better off just completely eliminating that. There is some nuance to that, obviously. If you're trying to clean a part that maybe has polymerized oil or carbon or other ionics or oxidation, maybe you do need that aqueous process upstage. But for everything else, you would be doing 2 cleaning steps to ultimately dry your part. And so let's just go with 1 cleaning step that also dries in the same exact process. And with that, I will turn it back over to William. Thank you.
Thanks, Ethan. Thank you guys for watching this Tech to Tech session. If you would like to discuss this topic further or have any questions not answered in the session, please contact your local KYZEN regional manager or send an email to tech@kyzen.com, and we will have someone follow up with you as soon as possible. And if you like this video, be sure to follow us on our social media platforms for more expert cleaning content.